Good morning. This is our fourth lecture on X-ray crystallography and solid-state chemistry. In the third one, we discussed symmetry elements. And then we talked about point group a little bit. But now we have to discuss point group as well as space group in details. And that is the key points to understand three-dimensional X-ray structure of a crystal. Therefore, we take a little bit more time to let you understand this a bit clearly, maybe not perfectly clear, but a bit clearly. So we say that symmetry elements may occur alone or in combinations to each other. And that created 32 unique crystallographic point groups. That for 7 crystal systems. That's what the last sentences in the third lecture. Well, you see, we have 7 crystal systems, as you know very well. The point groups of those 7 crystal systems are derived mathematically and found that each system has definite point groups. So in triclinic, we have 2 point groups. One is only one point group, and then one symmetry element. That means we have a 360 rotation to get our equivalent position. But in that case, we have to have also another point group which created by center of symmetry. And that's what we always describe as bar one. In some books, it is written -1. Maybe for typing easiness, the bar 1 is represented as -1. That is always a centrosymmetric point group. Of these, I'll go to the next slide, and here, one thing, we say it may occur alone or in combination. So this is a point group occurring by a symmetry element alone. This one is alone. This one is a mirror plane alone. This one is inversion center alone. But a combination, this is a combination of point group. 2, 4, as well as a mirror plane. This is a combination of point group. You see, 3 perpendicular, 2 fold axes. This is a combination of another point group, 2 mutually perpendicular mirror plane, and a 1 2-fold rotation axis. So these are how we represent it. Now we go to the next slide, and then you see we have 32 point groups. Of these point groups, 11 are centrosymmetric point groups. These centrosymmetric point groups are also known as Lau symmetry, or Lau classes. Then what is centrosymmetric point group? It must have an inversion center. What do we mean by inversion center? Let's say takes a point in a unit cell, and its coordination is x, y, z. For example, if we have an inversion center, we get another indistinguishable point, -x, -y, -z. I repeat, these sometimes shows as bar x, bar y, bar z. So the 11 centrosymmetric point group are here, the 11 centrosymmetric point group. This point group must have a inversion center, must have an inversion center. That's why symmetry elements we are talking here is center. Next, we say center as well as axis, can be a plane, etc. So centrosymmetric point groups are characteristic point group of crystal systems. I come to it in next slides. Okay, non-centrosymmetric point groups. So we have 11 centrosymmetric point group and 21 non-symmetric centrosymmetric point group. Non-centrosymmetric point group means that it does not have any center of inversion. Well, next slide, you see, we have to explain a little bit and say how could we represent these point groups in a paper. So we have to follow some rules for that. In the right one, this is a stereographic projection of a point group. Let's now talk about this one. It seems to be a crystal, is it not? So, and if we have an idealized solid and it has faces, then we call that an ideal crystal. So this is an ideal crystal. So what happens in ideal crystal? The X, Y, Z are the axes by which we will define this ideal crystal system. Faces are then reflected by XY plane, XZ plane, and YZ planes. So there are three mutually perpendicular planes. This is one a plane, this is a plane, this is a plane. So this is mutually perpendicular planes, and the intersection of these three mutually perpendicular planes are said to be origin of the coordinate system. Here, what we are showing in B shows point related by symmetry operation. If we have a symmetry operation along this x-axis, we have the points which are related here. So this is a mirror plane. We get this group of points exactly equivalent to this group of points due to a mirror planes. So what we have then, we can show that we have four in this 2 points here, 2 points here, 2 points here, 2 points here. These are called equivalent points due to the operation of mirror planes. Two mirror planes, we have equivalent point. Okay, so we go, and one more thing, that the point which remains unmoved by the symmetry operation, this is usually the origin of the coordinate axis. This one is unmoved. This one is unmoved. Then this one is unmoved if we give a symmetry operation. Therefore, these are said to be taken as origin. Next, we are coming to represent some of the point groups out of this 32. And we say that symmetry element alone can form a point group or in combination. In these figures, I'm showing alone a symmetry element 2-fold rotation axis, a symmetry element 3-fold rotation axis. So stereographic projection, what it is in the right hand of the figure. What is the stereographic projection for a 2-fold rotation axis, which is perpendicular to the plane of the paper. So this is one 2-fold rotation axis shown by this figure, and this one is called stereographic projection of a 2-fold rotation axis. And due to this, we have equivalent position. So let's say we start from 1, and after 180 degrees, we get 2. These are two equivalent positions. This one is indistinguishable with this one. So we create a equivalent position having a 2-fold rotation perpendicular to the plane of paper. If we go to another point group 3, so we have a 3-fold rotation axis. We show this by this projection, and this is stereographic projection of a 3-fold plane, 3-fold rotation. Due to this 3-fold rotation, we have equivalent position, 3 equivalent position. And that means once we have this one, the starting point, after 120 degrees, we get the 2, which are equivalent to each other. And then another 120 degrees, we get 3. So these 3 points are equivalent position if we have a 3-fold rotation. Now we go to mirror plane. And only one mirror plane would have a point group also. In monoclinic, we have a point group N. That is, we have a mirror plane. And this is shown in these 2 figures. Now depends on how this mirror plane is projected. Is it perpendicular or is it in the plane of paper? If it is oriented in a plane of projection, then we show this stereographic projection in a thick circle. That means that we have the mirror plane in the plane of projection. And due to this mirror plane, the plane of projection, we get 2 equivalent points. One is lying below the other. Below. If this one is above the plane, the other one is solid circle, the other one is below the plane. That are the 2 equivalent points projected due to this mirror plane in plane of projection. Now we take another orientation. If we have a vertical mirror plane, which is perpendicular to this circle, we show it in a dark, thick line bisecting the circle. And therefore, we get 2 projection there, 2 equivalent position. That's 2 equivalent position. So these what we are showing the mirror plane point group, mirror plane point group, and their stereographic projection as well as the equivalent position. You might be asking, why then? How do we apply these to molecules? In next slides, we will show at least 2 examples how we apply it in the molecules. Here we said we have a centrosymmetric point group, and that must have a center of symmetry. Must have a center of symmetry. So we have a centrosymmetric point group here, bar 1. Bar 1 has no stereographic projection sign. So we do not have 2 figures for bar 1. We do have only 1 figure for bar 1 because that is the stereographic projection as well as equivalent position shown in this circle. So mind it, for bar 1, we do not have any stereographic projection like others. So here is a projection of a bar 3. Bar 3 means that we have a center of symmetry as well as 3-fold rotation. So for 3-fold rotation, here we are showing this stereographic projection by a triangle, and since it has got an inversion, therefore in the triangle we have an open circle. So for this point, we generate 6 points due to this inversion and 3-fold rotation. We generate 6 points, and these are the 6 points for the equivalent position of this bar 3 point group. So far we have been talking about symmetry element alone having a point group, but we didn't take any combination yet. So we take the combination of symmetry elements. Let's talk about this figure. And step 1, we have a 2-fold rotation axis perpendicular to the plane of projection. And due to this 2-fold rotation axis, we get 2 equivalent positions here. 2 equivalent positions. Then the step 2, we have another 2-fold rotation. How do these lies? This is the 2-fold rotation. This side, this is the 2-fold rotation. Parallel to the plane of projection, and that what creates another 2 points. These 2 points have been created by this projection. Then the third step, we have another mirror plane, vertical mirror plane running through this, bisecting this plane of paper. So these are exactly equivalent, and that this did not create any other equivalent positions, the same position. Due to this one and this one, we immediately create another twofold rotation. So this is a stereographic projection and equivalent position of a 2-2-2 point group. Now I say that we will be taking an example of molecule and show how we are showing the stereographic projection of the point group. So we take a methylene dichloride molecule. This is methylene dichloride, and this is the structure of a methylene dichloride molecule. So you see, we can bisect this H, C, H angle and C, Cl, Cl angle by twofold rotations. Twofold rotation. So there is a twofold rotation. Perpendicular to this, we can bisect this molecule. And then we have two mirror plane also, is it not? Here is one mirror plane horizontal and another mirror plane vertically. So our point group should be MM2. And due to this symmetry or element operation, we should have 4 equivalent positions. But unfortunately, see here only 2 equivalent positions. Why this? This is because that we have general equivalent position and spatial equivalent position. If the equivalence position fall on the symmetry element, in this case, it falls on the symmetry element, that's mirror plane. Therefore, these are spatial equivalent point. And this spatial equivalent point, 4 equivalent point reduced to 2 equivalent point for spatial equivalent position, for spatial equivalent position. You see, MM2, here we are talking about MM2, and you can see you have these equivalent positions are not in and on any of the symmetry element. Therefore, we have 4 equivalent positions. As soon as it is on the symmetry element, equivalent position, then it reduces to, the 4 reduces into. We take another example of a molecule. This is a methylene chloride molecule. So if we take methylene chloride molecule, you see here we have methylene chloride. We can immediately see that we can have a 3-fold rotation. As well, 3-fold rotation. If we rotate in this axis, we can get this molecule after 120 degrees, exactly identical. Then this is a 3-fold rotation axis. And then we have a mirror plane along this axis, along this axis, along this axis. So mirror planes are shown here, here, here. So for 3-fold rotation, if you remember, we have 6 equivalent positions. But then one of the equivalent position lie on the mirror plane. Therefore, it is reduced to, since it has got 3 mirror planes, therefore it reduced to 3 equivalent positions. So this is how we explain the point group and present it stereographically. We have 32 point groups, and if you go to International Table of X-ray Crystallography, earlier edition, probably, I said earlier edition, later editions, there are some specific things which an experienced crystallographer needs. But say in elementary crystallography, we need the earlier edition where only these sort of things are discussed. Well, we go to then a table. Here, I'll take a little bit time. I say that we cannot define crystal system only with unit cell parameters. It is one of the points to describe, but it is not the only one. We have other things to be taken into consideration. For example, symmetry elements. So with space symmetry elements, a cubic crystal system must have this point group. If it doesn't have this point group, we cannot call it cubic. It may show as pseudo-cubic, but unless and until it has got this symmetry elements, only then we can say that this is a cubic system. Similarly, for tetragonal system, we must have this 4-fold rotation and 3 perpendicular mirror plane to each other. For hexagonal, we have this symmetry element, symmetrical point symmetry group, which say that it must be hexagonal crystal system. And this is bar 3M, which is rhombohedral setting. For this, we must have a bar 3M to say it is a rhombohedral crystal system. And then this is already I told you, this is a hexagonal setting for rhombohedra. So it must have this symmetry element. Similarly, orthorhombic, this must have to be symmetry element. And then monoclinic, and then you see triclinic, bar 1. These are the symmetry elements must be present in the crystal systems to identify they are real crystal system. Okay. There, if you remember, we said that we have lattices, 14 Bravais lattices. So cubic system must have primary lattice point, face center lattice point, body center lattice point, primary lattice point, and so forth. You see, there are 14 Bravais lattices, which have also another parameter to consider for cubic, tetragonal, hexagonal, and etc. Okay, so with this, we go to the next slide is, with this slide, we have to finish our 4th lecture of crystal system, crystal lattice and crystal systems. I said again that it needs a little bit time to understand these because most of these are 3-dimensional things and we are talking about 2-dimension, and then always having in mind that we have another dimension to consider to discuss crystals. Thank you very much. We continue our 5th lecture with symmetry elements, and that will be space symmetry elements. And we go for space group then. When we understand point group and space group, it will be very easy for you to understand crystal systems. Thank you very much.